Hello everyone, my name is Ali-Ayman and I'm an electrical and electronics engineering student at the University of Edinburgh. Today, this will be the beginning of our brand new series on atomic structure, and this will form a much longer series I'll be making on physical chemistry. So if that interests you, and if you're interested in, maths, physics, chemistry, economics, finance, self-development, all that kind of stuff, there'll be plenty of that coming, so stay tuned. Today we'll be looking at fundamental particles. All right, so we'll start off. So when we talk about fundamental particles, we're talking about the atom. The atom is basically the smallest particle of matter that makes up all things, and it cannot be broken down any further by chemical means. Meaning we cannot heat it, we cannot, physically destroy it with like a hammer. We cannot break it down using any kind of, physical means we have to do so. Um, and the theories surrounding, the nature of the atom or the model we associate when we talk about, the atom over the last 2 centuries, there have been many, theories even before that. Let's look at some examples of what these models, these earlier models from like 200, years ago, more recent, models, not the ones from way, way back, but the more recent ones. Let's look at some theories that were devised over the last 200 years or so. So we start off with a guy called John Dalton in the 19th century. What he proposed was that elements were composed of small, hard, and indivisible spheres, which cannot be broken down any further. And he also said that all the atoms of an element had the same relative masses, and that atoms of different elements had different masses. Now let's unpack this. First of all, what is an element? Element is a substance which contains only one kind of atom or one type of atom. And if you're interested in elements, we will be making, more videos on, the nature of elements. All the elements that, are known to us are listed here in what is known as the periodic table. And, the characteristics of the periodic table, what the different groups entail, the different properties, different reactivities going up and down and across. We'll be making videos on that, so stay tuned for that. So that's what elements are. Elements are basically substances made up of the same kind of atom, or sorry, only one type of atom. Only one type of atom makes up an element. So this is what Dalton essentially proposed, that elements, okay, were composed of small individual atoms or spheres. When he says spheres, in our context, we're basically, talking about atoms. And the diagram, for his model is, basically like this. We've got a regular arrangement or regular lattice of hard spheres, as Dalton said, and it's very difficult, to break them. They are, small, hard, and as we said, indivisible. All right, and he also said that all the atoms of an element have the same relative masses. So the masses of the atoms in an element were all the same, and the atoms of different elements had different masses. Now, is this correct? If we take, the theory as a whole, in its entirety, it's not quite correct. But there are some correct, aspects of it. One is that yes, atoms are, you know, uh, indivisible. They are indivisible. Um, Spheres is a bit too general. They're not really spheres. We'll look at exactly, what they are, but and yes, they are small, but they're not necessarily spheres. But yes, they are indivisible, and yes, they cannot be broken down any further. But this is and yes, the other points he made about the atoms of one element all having the same mass and atoms of different elements having different masses. Again, that's all correct, but this is far too simple model, it does not go into detail as to what atoms actually, what atoms are actually made of, and the different forces of attraction acting within atoms and between atoms, which causes them to be held in that way, and so on and so forth. It's a little too simple, and again, also the sphere analogy and the hard analogy. It's not really the most detailed, but again, it was on the right track. Now I'll just summarize what I've just said down in this section here. All right, the next scientist who proposed the theory that we'll be looking at is somebody called J. Thomson from the late 19th century, 1896. So basically, after discovering the electron, pause here, an electron, if you don't know what that is basically a negatively charged particle. So it's a negatively charged particle, and we will be talking about this in more detail below. So basically, Thomson concluded that an atom consists of a sphere of positive charge. Let me start drawing it out now so that you can see what I mean. So it consists of a sphere of positive charge, a sphere which has positively charged, evenly distributed everywhere, with electrons embedded in sort of like circles within the sphere, like if you'd like, very similar to how plums in a pudding are embedded, hence the name, the plum pudding model. That was the name of the model that J. Thomson came up with. So electrons, Thomson said that the electrons are embedded in the sphere of positive charge. And again, very similar to how plums in a pudding are embedded. So these in blue are the electrons, and the white crosses symbolize the sphere of positive charge. Now, let's talk about the correctness of this model. When compared to the actual model, again, this model is not correct either. It's not fully correct because one, in the actual model, electrons are not embedded in a sphere of positive charge, and an actual atom doesn't even consist, of a general sphere of positive charge like this. So this model was not the correct one, and it also contradicts the later findings of people like Ernst Rutherford, and later on we'll talk about in another video of Niels Bohr. So this model was not correct. And I'll also, summarize this to, help. And I've summarized the correctness of the previous model here, in case you want to look at that. Okay, so that's the J. Thomson model summarized. One point I forgot to mention was that one correct thing about this model was that it was the first time the existence of positive and negative charges within an atom was actually acknowledged. As I mentioned before, this was not the case with John Dalton's model, and certainly not the case before John Dalton. So one correct, aspect of J. Thomson's model was that this was the first time the positive, negative charges within an atom were first acknowledged. Now let's look at the last model we have here from somebody called Ernst Rutherford in the early 20th century. So after conducting a series of alpha scattering experiments, now, what are alpha particles? Alpha particles are basically helium nuclei. Again, we'll look at this further in later videos, and it's a type of ionizing radiation. So it's emitted by radioactive sources. What Ernst Rutherford did was he fired alpha particles at a gold sheet. So he essentially used a source of radiation. He used a source of radiation to fire alpha particles at a gold sheet. And he basically recorded the observations he found as a result of this experiment. This basically just symbolizes the alpha particles. It's the symbol for them. And the results of this the results of these experiments were as follows. So basically, he found out that most of an atom was mainly empty space. So most of an atom consisted of empty space. So why did he come to this conclusion? He came to this conclusion because most of the alpha particles in this experiment passed straight through the gold foil. So most of these alpha particles passed straight through the gold foil unaffected. Rutherford's second observation was that at the center of every atom there was a positively charged nucleus. The last conclusion he came up with was that this was where most of the mass of the atom was located. So the center of the nucleus, so the center of the atom, i.e. the nucleus, was where most of the mass of the atom was located. So this was also where most the mass of the atom was located. So how did he come up with the conclusion that all atoms at their center had a positively charged nucleus? Well, a small percentage of the alpha particles fired at the gold sheet or the gold plate were actually deflected. And some were deflected at angles, and some were deflected at 90 degrees. So that's how he came up with the conclusion that there was a positively charged nucleus, and it was also where most of the mass of the atom was located, because because before he came to the conclusion that most of an atom was empty space. Why? Because most of the alpha particles passed through the gold foil unaffected. Now, if we were to illustrate Rutherford's model of the atom in a diagram, it would look something like this. So most of the mass of the atom was at the center, and all atoms had a positively charged nucleus at their center, and most of the atom was considered empty space. And this model of the atom very closely resembles the one we have today, because yes, the fact that most of the mass of the atom was empty space is correct, and yes, atoms do contain positively charged nuclei at their center, and the center is also where most of the mass of the atom is located. So the only issue with this model would be that the details surrounding electrons and the electron arrangements around the positively charged nucleus were not very detailed. And also it would take more alpha scattering experiments to conclude that neutrons also existed. We'll talk about neutrons later on, but the existence of neutrons was also missing from this model, but would soon be rectified after more alpha scattering experiments had been done. So the conclusions we can come up with from these different models of the atom from the last 200 years or so is that because of Rutherford's experiment, it has been known for many years that atoms are made up of smaller subatomic particles. So what do I mean by this? Well, atoms as we know them, these small indivisible particles that make up everything, well, they themselves consist of even smaller particles which make up the atoms themselves. And there are three different types of subatomic particles, which we'll talk about here. The first one we have are protons. So protons have a relative charge of +1. So when we talk about relative charges, we're talking about the charge of this subatomic particle, protons, compared with neutrons and with electrons. So when we compare the charge of protons with the other two subatomic particles, we get +1. Protons are positively charged. Their relative mass, so their mass compared with the other subatomic particles, is 1, and their location is inside the nucleus. Okay, now for the neutron. Neutrons are uncharged particles. So neutrons have a charge of 0. Their relative mass is the same as that of a proton, or they have basically the same masses. So the relative mass is also 1, And again, the location of neutrons are also inside the nucleus. Now, for electrons, electrons are negatively charged particles. They have a relative charge of -1, and their relative mass compared to protons and neutrons is very, 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 very small. And it was only until very recently that the mass of electrons was actually able to be determined. But basically, if you really compare the numbers and we compare the mass of an electron to that of protons and neutrons, it's around, something like 1 over 1,800 or something like this. It's very, very, very small. Now, the location of electrons is around the nucleus. Electrons orbit the nucleus of the atom. So what does this mean now in terms of the actual model of the atom we have today? What is the arrangement of subatomic particles inside the atom, and what does the atom actually consist of? Let's start off with what atoms consist of. So atoms basically consist of a positively charged nucleus at their center, which contains both protons and neutrons. So as we said, atoms consist of a positively charged nucleus at their center, which contains protons and neutrons. And another thing is that the reason why protons and neutrons are called nucleons is because they are located in the nucleus of an atom. So it's just, it's a convenient word to have. The protons and neutrons are also called nucleons because they are located within the nucleus of an atom. And you may wonder now, you may wonder, another concept I haven't mentioned earlier is that like charges repel and unlike charges attract. So positive and positive charges will repel, and positive and negative charges will attract. Obviously, same with negative and negative charges, they'll also repel. But in the case of the nucleus of an atom, we have just said that a nucleus of an atom contains both protons and neutrons. Although neutrons are not charged, protons are, and they're positively charged. So so you would think that there would be electrostatic repulsion between the protons in the nucleus of an atom. But in fact, there isn't. There is an attractive, what we call strong nuclear force, which acts between the nucleons, i.e., between the protons and the neutrons inside the nucleus of an atom. There is what we call a strong nuclear force which acts between them and essentially keeps the nucleus of all atoms intact. Hence why the nucleus of all atoms doesn't disintegrate because of electrostatic repulsion. And this strong nuclear force overcomes the repulsive electrostatic force of attraction that acts between the protons of like charge. So since the strong nuclear force is stronger and overcomes the forces of repulsion between the protons, that basically allows the nucleus of atoms to remain intact. Now, around the nucleus of an atom, we have electrons. We have electrons which orbit the nucleus of an atom. Obviously, electrons are negatively charged. And again, the more details on the arrangement of electrons within atoms are going to follow in the next video, so stay tuned for that. Now let's talk about the arrangement of subatomic particles in the atom using diagrams. So we said that atoms contain protons and neutrons inside the nucleus of the atom. And again, the nucleus of the atom is where most of the mass of the atom is located. So just this I'm not trying to, draw an actual or represent an actual, atom of a particular element, but just for you to get the idea, in the center of the atom, we have positively charged protons and uncharged neutrons, all, together here with the strong nuclear force acting between the protons and the neutrons, which prevents the actual nucleus of the atom from disintegrating. which it would disintegrate had this strong nuclear force not been there because of the, as we said, the electrostatic forces of repulsion that exist between particles of the same charge, in this case, the protons. And around this nucleus, we have, as we said, negatively charged electrons, which orbit the nucleus. So because the number of protons is equal to the number of electrons in an atom, atoms are always neutral. They have no overall charge because the positive charge of the protons cancel out the negative charge of the electrons, and we end up with an atom which has an overall or net charge of 0. All right, so here's some very small, very easy practice questions for you to have a go at. So use what you've learned in this video to try and answer these questions. So right now, I would like you to pause the video and try and answer these questions, and let's see how you get on. Okay, so question 1a part I, or question 1a asks, which of the following protons, neutrons, or electrons are nucleons? Well, nucleons, as we said, are the subatomic particles we find in the nucleus of an atom. And as we mentioned before, these are protons and neutrons. Now for part II, which of the following subatomic particles have the same relative mass? Well, the answer to that is also protons and neutrons. They have the same, relative mass, and they're both also found, as we said before, in the nucleus of an atom. Now for part III, so which of the following have opposite charges? Well, we said before that neutrons have no charge, protons have a charge of +1, and electrons have a charge of -1. So the subatomic particles with opposite charges would be protons and electrons. Now for part 4, which have no charge? So which of these subatomic particles has no charge? As we said before, that would be the neutrons. And which of the following are found outside the nucleus? Well, that would be the electrons. Now for part B, we have to explain why we assume that there are the same number of protons and electrons in an atom. Well, the answer to that is that atoms have an overall charge of 0. Atoms don't have neither a positive charge nor a negative charge. And why is that? Well, that would have to be because the total positive charge of the atom would have to cancel out or be equal to the total negative charge of the atom. So we say that atoms have no overall charge because the total positive charge and the total negative charge of an atom must be the same for them to cancel out. Must be the same for them to cancel out and make the overall charge 0. Okay, so this is the end of the video. I hope this all makes sense and you've learnt everything just fine. If not, rewatch what you haven't understood from this video. Look at the resources I'll put in the description. And if there are any questions, don't hesitate to ask. And stay tuned for more videos on this series and those from other series which will come. And if you like this kind of content, please subscribe, like, and share. That would really be appreciated. So I'll see you in the next video. Goodbye.